there's one more thing about a wave that I want to talk about. Thing, bad word there. Essentially, another way to describe, but in this case, we're not going to describe the entire wave, but we want to start talking about individual points in the pattern. So we'll get there eventually. The word that I'm going to be introducing is something called phase. But we have another thing that I want to talk to prior to that. So I'm going to share my screen. We're going to look at a demo and go from there. Okay. So if I have this simulation, which can be found by Googling PHET, P-H-E-T, waves in a string, if you want to look at it yourself. I've got a motor here that is making transverse waves, right? Because it's moving up and down, and the wave energy is propagating to the right. Okay. And it's very mesmerizing to look at. Interesting little thing, I can change the frequency, the amplitude, the tension. So by changing the frequency, I'm changing the source, which changes the wavelength. I'm changing the tension, which changes the medium, which changes the speed, which changes the wavelength, and the amplitude, which changes the work done per cycle. Not what we're talking about. So I'm going to pause this for a moment and I'll hit slow. So the question I have is, we saw that the source was moving up and down, so the wave energy was propagating to the right. Therefore, since this is a transverse wave, all the particles in the medium are also vibrating up and down. They mirror the source, but just at a lag. So the question I have is, if I examine this point in the medium right here, and I ask, what direction will that point on the medium move next? And I'll stop the video for a second and you can think about it. All right, so hopefully you thought about it. And so let's talk about wrong answers. So a wrong answer here would be left or right. Well, why is that a wrong answer? Well, let's think back to the fundamental nature of a transverse wave. A transverse wave is one in which the particles of the medium vibrate perpendicularly to the direction of energy transfer. So we said the direction of energy transfer here was clearly to the right. Therefore, the answer to this cannot be right or left because then the particle of the medium would be vibrating along the same axis as the direction of energy transfer, which is what happens in a longitudinal wave. But that's not what we're talking about. We're talking about a transverse wave. So the question here is up or down, or the right answer here is up or down. So what is it, up or down? Well, we're keeping an eye on this one here, and I'm gonna advance the frame because it goes too quickly if I just let it go. You have your answer in your head, and there's the answer. That point moved downwards. So is that what you expected or not? Well, a lot of people have difficulty with this skill because they're so taken by the fact that the energy is propagating to the right. They say it's going to want to go and think towards the right. But really, what we're thinking about here is that the pattern is translating from the left to the right. So this point in the medium doesn't care about what already happened to it, but what's about to happen to it. Like if I were to ask you to cross the street on a one-way street and said, how would you figure out how to be safe? You wouldn't tell me to look in the direction the cars are going. You would tell me to look in the direction opposite that they're going so I could see what's coming next. So that's the key of this. Notice this pattern is translating to the right. So what's coming next for this point is the trough of the wave. So this point has to move downwards to become the trough, which is what happens. If I say what's happening next to this point here, we'd say, oh, the crest is coming next for that point. So that point is going to move up next. If you think about the wave in a stadium, right? You look in the direction that the people are standing up, opposite the direction the pattern is moving. And I know that first you're going to have to stand up to become the top of it, and then you're going to sit down to become the bottom of it, right? Same sort of idea. Now, why are we talking about this with respect to phase? I'll tie it in a couple of minutes just so we can see this. All right, so we're going to be thinking about this picture here of a transverse wave, and I'm just going to get it to specific point. Okay, so now what this does is it looks like a sine curve. Okay, everyone kind of agree with that, right? At 0, 0. I'm pointing at the screen with my finger as if you can see it, and 0, 0. On the axis here, I go up to the maximum, and there you go. Okay, I'm going to flip over to my visualizer here. I have that same picture there, right? And if I were to ask you, if we were in a math class, to label the parts of the sine wave, I think you would know what to do. This part of the sine wave, we'd say, oh, that's the beginning. That's 0 degrees, right? And then what point is this? Well, in the pattern, this is 90 degrees. Or if we're going to be more formal, we could do this in radians, and that would be pi over 2. Okay? Here, following that pattern, that's 180 degrees, or pi. Here, 270 degrees, or 3 pi over 2. Here, 360 degrees, or 2 pi. Here, 450, or 5 pi over 2. Here, 540 degrees, or 3 pi. Here, 630 degrees, or 7 pi over 2. Here, 720 degrees, or 4 pi, right? 4 pi, which is, of course, is 8 pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2, so on and so forth, right? These numbers are the phase. So the phase is just the quote unquote position along the pattern in degrees, whether that's degrees radians or actual degrees. There you go. Now, why do we care about phase? Well, here's where it gets interesting. If I look at these 2 points here, the point at the phase of 90 and the point at the phase of 450. So those are both crests, right? Come here, that's this point here and this point here. If I were to ask you, what what are those points going to do next on here? I think we can see that for this point here, the trow is coming, so it's going to move down. For this point here, the next trow that this is going to make is going to arrive. And so both those points would move downwards. But if I keep an eye on those 2 points, not only do they move downwards, but at all points, so I'm talking about these 2 points here, right? Notice that their motions are exactly identical at all points in time, right? So that when they vibrate exactly like this in sync with one another, okay? And that's where the idea of phase becomes really powerful. So that's these 2 points. Those 2 points would vibrate in exactly the same way. If I look at it, these 2 points here, they're both going to become the crests. They would both move up and then down and up and down. Those 2 points would vibrate in exactly the same way, at exactly the same time at all points. And so we're going to say that those 2 points are completely in phase with each other. Okay. And these are 2 points on a medium whose vibration, I'm going to close my window because there's noise outside, whose vibration is exactly identical at all points in time. Okay. Now, that's what they are, but how far apart are those points? If you notice, those 2 points, those 2 points, those 2 points, every single time I'm doing that, that is exactly one wavelength apart. But notice also, this crest would also do exactly that. Oh, let me give this is 810 or 9 pi over 2, right? Would do that as well. And so points that are completely in phase are separated by one wavelength, two wavelengths, three wavelengths, or we'll say n wavelengths, where n is an integer. Okay. But from a phase standpoint, we'd say that those points have a phase difference of n times 2 pi or n times 360 degrees. And really, that's what we care about, is this concept of phase difference. So points that are completely in phase have a phase difference of 0, 360, 720, right? 0, 2 pi, 4 pi, 6 pi, 8 pi, etc., right? Um, that's going to become really important when we talk later about the concept of interference. Because if two points are exactly doing the same thing, and if I have two waves that are doing exactly the same thing in exactly the same place at exactly the same time, i.e., they are in phase with one another, that's going to do something really interesting. That's going to be called constructive interference, but we'll get back to it. Now, if we have completely in phase, it makes sense to talk about 2 points that are completely out of phase. And these would be 2 points, hopefully you can guess the definition, that rather than do exactly the same thing at all moments in time, that their motions are exactly opposite at all motions at all points in time. So take a guess. Which 2 points here are out of phase with one another? And hopefully you said a crest and a trough would be, right? Because this crest is going to move down to become a trough. This trough is going to move up to become a crest, and they would do that, okay? Also, these 2 points, right? This is moving up to become the crest. That's moving up to become the trough. So if we're talking about things that are completely out of phase, okay? So completely out of phase, these are 2 points that are whose motions or vibrations are exactly opposite at all moments in time. Okay. And hopefully you can see how far apart are those. Well, this and this, that's half wavelength, right? But what's the next point that would be out of phase with this? Well, a half wavelength later, I'm at a crest. That doesn't work. So it'd be here, 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 it'd be another trough, which is 3/2 wavelengths, right? Or 5/2 wavelengths, 7/2 wavelengths. So they're separated by an odd multiple of half wavelengths. So we're going to have a way of saying that. We're separated by a distance of k times lambda over 2, where k is, whoops, an odd integer. So we're going to use k for odd integers for this. It's a standard math notation in some books. Okay. From a phase difference standpoint, this point and this point, if you notice, there's a phase difference of pi over 2 minus pi, pi, or 180 degrees. Between here and here, once again, 3 pi over 2, difference of pi, or 180 degrees. Or a phase difference of k pi or k 180 degrees, where once again, k is an odd integer, right? So the point of talking about phase and different points in the wave is really to compare different points and eventually to compare different waves so that we're going to have waves that are going to be completely in phase with one another and waves that are going to be completely out of phase, right? So now you may be thinking completely in phase, completely out of phase. What happens if they're not completely in or out? This course is not really going to deal with those moments, but those points will have, motions that don't exactly match with each other. They're not exactly opposite. Sometimes they're going in the same direction. Sometimes they're going in opposite directions. They're moving at different vibrational speeds at different times. But in phase points, if I were to draw a velocity vector representing their vibrational velocity, those velocity vectors would be identical in all moments of time. And if I draw out of phase, those two velocity vectors would be exactly equal magnitude in opposite directions at all points in time. So that is the concept of phase, and it's our last descriptor, not of the wave pattern, but in this case of individual points in the wave, so that when we have multiple waves, we're trying to describe how they're interacting, we can talk about this through the lens of phase. And so with that, I'm going to stop sharing my screen. And that brings us to the end of a description of waves, and then we'll be moving on to talking about the properties of waves next.